guys, welcome to 3.4 Cheapest Link Notes and Practice. This is our final section of the Traveling Salesman Problem, or Unit 3. Let's get started. So far, we've been considering the creation of a Hamilton circuit in order. Nearest neighbor travels like that, from the first cheapest, and then from there find the next nearest, and then from there find the next nearest. But what if we ignored going in sequential order? What if we look at the graph as a set of potential links between cities, and as long as we're careful that they're all connected in the end, doesn't really matter if at some point in the process they're disconnected. So here's some rules. Don't close your circuit until the very end, and we only need to go in and out of each vertex. So we're never going to have a vertex with degree 3 or 4, only ever degree 2. So if we have n vertices, we're going to end up with n edges in our final circuit. Here's our process. The first thing we're going to do is we're going to look at all the links in the graph and find the cheapest one available. If there's more than one as cheapest, then randomly pick one. And we're going to highlight that link. You can use red or really any other color. Then pick the next cheapest link. Highlight that. And then keep doing that as long as you don't close a partial circuit and don't create any vertex with degree 3. Finally, we'll connect the last two vertices that will close our circuit, and we'll have a Hamilton circuit that we can write from any starting point. Either clockwise or counterclockwise travel is going to give you a cheapest link tour. Let's take a look. We've got Willie Lomax going on his final journey. We can see here that 119 is the cheapest link in the entire graph. From there we look. 120, that's now the cheapest link. Of the ones left, you see that 121 would be giving C a vertex of degree 3, so we can't use it. The next cheapest link would be 133, but that would close a partial circuit, so we can't use that. That means that 150 is now the cheapest link, and we highlight it. Little tip, cross off the links that you can't use. It keeps you from getting confused later. All right, once we do 150, 152 is the cheapest link. And once we do that, we've got 174, but that would give both D and C degree 3 and would close a partial circuit, so no, not going to do it. We have 185 coming from A to B, but that would give A degree 3, so we can't use that. And so I'm going to go ahead and cross those off. $199 would give D degree 3. So the only thing left for me is E to B, this link here, and we're connecting it to finish. So a tour from A goes from A to C to E to B to D to A. And its weight is 119 plus 120 plus 200 plus 150 plus 152 for a total of 741. Now note how this still does not give you the optimal route from A, which has a cost of 676 from using the brute force algorithm. So again, we have a method that is efficient, but is only approximate, much like nearest neighbor. The brute force method is the only one that is truly optimal, but it is so inefficient. So far, no one has been able to produce an optimal, efficient algorithm for solving traveling salesman problems. On the other hand, no one's proved that an optimal, efficient algorithm is impossible. Maybe one of you will find it in the future. Let's do some practice. Let's use the cheapest link algorithm to find an approximate Hamilton circuit in the graph. Once found, we'll write it from point D and list its weight. Okay, the cheapest link in this graph is 3. So I am going there. Now, the next cheapest link in this graph is 4. The cheapest link is now 5, but note I can't use 5 because 5 would make E degree 3. No 5. What about 6? Can I use 6? I can use 6. All right. Next would be 7. Can I use 7? Yes, that makes C degree 2. What's next? 9. I cannot use 9 because that would make C degree 3. I cannot use 10 because that would make C degree 3. I cannot use 11. It would make both E and D degree 3. I cannot use 12. That would make D degree 3. The only option available to me is to connect B to A. So I am now going to write my circuit starting from D. From D, I could go to A or C. I'm going to go to A. And then B, E, C, D. You could have written D, C, E, B, A, D as well. That's the mirror circuit. Let's take a look. D to A is 6. A to B is 14. E to E is 3. E to C is 4. And C to D is 7. So, on my calculator, 6 plus 14 plus 3 plus 4 plus 7 is 34. And that is the weight of my approximate Hamilton circuit. Okay, let's move on. Use the cheapest link algorithm to find an approximate Hamilton circuit in the graph. Once found, write it from point Z and list the weight. Okay. The cheapest link I have is 10, and that connects X to V. My next cheapest link is 20, which connects V to Y. Now notice I'm just staying right in here. These are all duplicates. Okay, next, 30 connects X to Y. I can't use that. X to V, V to Y, and Y to X would be closing a partial circuit, so I cannot use 30. Next is 35. Well, that would be connecting V to something else. I cannot do that. Let's check 37. Yes, I can use 37. So right now I have X to V, V to Y, and Y to W. 42 is next. Would connect X to W. And I would have X to V, V to Y, Y to W, and W to X, which would close a circuit. Nope, I haven't used Z yet. All right. here would give me another link from V, which I cannot do. Here links Z to X. X only has one link, so yes, I can use that. And then X has two links, Y has two, V has two. Let's look here. 60 is next, Z to W. I can use that. And 77 I cannot use because Y already has two links. So let's take a look at how this is going to work. I want to start from Z. Z connects to W and X. We can pick one. I'm going to pick X. X connects to V. V also connects to Y. Y also connects to W. And W also connects back to Z. I've got my circuit. So now I'm going to add them up. 10 plus 20 plus 37 plus 50 plus 60. And on my calculator, I'll just add those up. 177 is the total weight of that circuit. Great job, guys. Now you'll be starting Unit 4, which is the unit I know you've all been looking forward to, the coloring unit. I'll see you then.